Assalamualaikum warahmatullahi wabarakatuh, and a very good day to everyone. Okay, today I am going to show you how to solve for indeterminate truss using force method. So the first step, similar to the one before, is to calculate the degree of indeterminacy. Okay, so the degree of indeterminacy for trusses, if you can remember, it's m plus r minus 2j. So number of members you have are 1 2 3 4 5 6. Your reactions are 3, pin and roller, minus 2 times j. J are the number of joints including the one at the support. So you have 1 2 3 and 4. So if you calculate, you will get the degree of indeterminacy as 1 degree, and with that you need to check whether it's indeterminate externally or internally. Externally indeterminate means that you have extra redundant support reaction, and internal indeterminacy means it has extra internal member as your redundant. Okay, so the way to check is by looking at your truss. First you try to remove the support reaction. In this case, let's try to remove support B and see whether it becomes stable or unstable. Since removing B will let you to become a unstable structure, hence your structure is internally indeterminate, means you have extra additional member that causing it to become indeterminate. So let's choose one of the internal member as your redundant, and usually is the diagonal. So let's choose AC as your redundant member. Okay, so as the method before this, what you need to do is to use superposition principle and draw the structure. Okay, let's draw this primary structure first. Okay, this is your primary structure. Imagine that you have cut member AC into two. You have cut it into two, and then you apply a unit load of 400 kilonewton, a load of 400 kilonewton, and this system is called your primary system. Okay, so when you have cut your member AC, when you load it, member AC cannot take any internal force. Okay, and if there is an member AC that have been cut, what happened is under this load, it is going to be separated. Okay, there will be a separation of distance between the cut points, and let's call this distance as delta AC 0. Okay, system number 0. Okay, and then as the method before, you then apply your redundant internal force. Okay, your internal redundant would be the internal member AC. Okay, so what you do then, for member AC, you apply an internal force, FAC. Okay, pulling force means its intention. So because of this force, this member, you have cut it into two, so this member is going to overlap, and the amount is delta AC1, because of system redundant number 1. Okay, and just like before, this redundant system can be represented by a unit load. Okay, so instead of applying FAC, you then apply a unit load 1. Okay, and the overlap will now become small delta AC1, and then you multiply the whole system by FAC. Okay, you will get the same system as your actual redundant. So we'll call this as your redundant system. And then you write down the compatibility equation. So the compatibility equation, you know that for your actual structure, the displacement of member AC is not there because it's one member. So delta AC, the original displacement is equal to the displacement of member AC when you make it as redundant. So delta AC 0, this is your primary system, plus your redundant system, which is delta AC 1. And again, since you have changed it into a unit load, it is also equals to small delta AC1 multiplied by FAC. Okay, so delta AC, because you know it's originally 0. Okay, so in order to find out what's this displacement, okay, what you need to do is to use a virtual method. If you still remember, virtual method says that delta is the displacement is equals to summation of big N, small n L divided by AE. Okay, for member AC, so the displacement of AC system 0 is equal to the capital N. Capital N is the internal force of all the members under the primary system, okay, this system. The second N is the internal force due to its virtual system. Your virtual system is your redundant system, so this is small n. Length L divided by AE, cross-sectional area and modulus. Similarly, you can also calculate small delta AC. Small delta AC 1, it will become N and L divided by AE. Okay, the internal force due to its own system, which is your redundant. The second N is the virtual, which is coincidentally also its own system. So that's why it becomes small n L divided by EE. Okay, so what you need to do is then find the internal force, and this is why I ask you to read on method of joint, the quick method, because you need to do it twice. Okay, so this is your primary system. Okay, you're applying a force of 400 kilonewton. Okay, this is 8 meters and this is 6 meters, and I hope you will try to do it really quickly by your own, and make sure you can get the same answer. Okay, and this is your redundant system. Redundant system is where you apply a unit load. Okay, and then can you please try on your own to find the internal force. I hope you can try using method of the quick method that I teach you in last semester. Okay, so if you do that, sorry, I didn't prepare this, but if you do that, you will get these forces. Negative means it's in compression, positive means it's tension. And again, please try it. Okay. And for your redundant, similarly, you will get some values. Okay, I'm obtaining this from just from the method of joint. Okay, I hope you can find it in your own leisurely time at home. Okay, make sure you know how to find all the internal forces. Okay, next is you form a table. So you form a table. I have formed a table for you. Okay, this was my table that I do it using Excel. So the first column is your member. Okay, so I have member A, B, C and D. Okay, so my members are AB, DC, AD, BC, BD and AC. L is the length of each member, so accordingly lah. N is the internal force due to primary system. This is capital N. Okay, so all of these values I plug inside, okay, except for member, wait, let me see, I think I typed this a little bit wrongly. So AB, DC, AD, B, okay, so it's correct. So except for member AC, AC is the diagonal member where you have make it redundant, you cut it, so the capital N would be 0 here. Okay, and then you just put all the other values in. And then for small m, this is the internal force under redundant system. You put all the values in from your redundant system, and again you are applying a tensile force of 1 at member AC. So if you look AC, the value is 1 here. Okay, all the others you just tabulate using virtual principle that you have learned before. Next, you calculate what's capital N, small n multiplied by L. Okay, this will give you, if you divide this by AE, this will give you delta AC 0. Okay, summation N and L divided by AE will give you delta AC 0, and then the second column will give you small delta AC 1. Okay, and then what you do, you sum them up. Okay, when you sum the whole column up, capital N and L, you will get a value of negative 11,200. Okay, and for small n, you will get a value of 34.56. Okay, and then you plug it back into the original compatibility equation. So compatibility equation was delta AC equals to delta AC 0 plus DAC 1 multiplied by FAC. Okay, so AC is 0. Delta AC is the summation of N and L divided by AE. Small delta is summation of N and L divided by AE, and then you have FAC. Okay, so solving this, you'll get 11,000. This is negative, sorry. So negative 11,200 divided by AE plus 34.56 divided by AE multiplied by FAC. Solving this, you will get your FAC equals to 324 kilonewton. Okay, and if you look back at your redundant system, since the redundant system is applied unit load is in tension, so whatever positive value that you have means that it is in tension. Okay, and then finally you need to find out what's the internal force of all of the other member. So this is very easy. So what you do is you extend your column. Okay, so extend your column. Okay, this will be the internal force Fi. So Fi, your method of superposition just now says that the actual structure will be equal to the internal force capital N for system N plus your redundant system here, small n, multiplied by FAC. Okay, so if you follow the same rule, okay, for member AB, F of AB would then be equal to 400, the internal force of the primary system, plus small n, the redundant system, multiply by FAC, which is 3 to 4 kilonewton. Okay, this will give you a value of 140.8 kilonewton. You repeat for all the members, you will get a value as shown here. Negative 194.4, negative 176, and 324. Okay, and that's the answer that we wanted, which is the internal forces of all of the member. Okay, with that, this is the method of force method for indeterminate trusses. With that, thank you very much.